from the previous video recorded section, we learned about the tree can be used for the arithmetic expression, and then how we can use the tree for the decision process. So we have the internal nodes and we have the external nodes. Okay. So do you know what is internal node? Internal node. So the internal node is a node that has children. So something like this one a fast meal. So there is a question about yes or no answer. So if it is yes, then you will go to the left. If it is no, you will go to the right. And then the external nodes is the node without any children. So this is the decision. And like this one, for example, do you want coffee? Yes, then you will go to Starbucks. So the decision will be Starbucks. If you want to go to Spike, then this is another restaurant name. And this is also another restaurant. Also know if it is on expense account. So it means it's maybe a little bit expensive. And yeah, the Cafe Paragon is also a name of restaurant. So this is the decision. Where do you want to have your dinner? Okay. So the concept of tree can be seen like this one. There are some notations that you need to understand to know about the tree. We have N, E, I, and H. Okay. N is the number of nodes, and then E is the number of external nodes, and then I is the number of internal nodes, and H is the head. Okay, I hope by now you already know what are they. Okay, so we have N is the number of nodes, so it is the total node. Okay, so E is the external node. So the external node is the node without children. Internal node is the node with children. Now we can have the properties. E equal to I plus 1. Oh, by the way, this is the properties of proper binary trees. Do you still remember what is proper binary trees? Proper binary trees. If you take a look on the okay, this is binary tree. So binary tree is a tree with at most 2 children. And if it is exactly 2, then you have proper binary trees. So for every node that has 2 children, you can say it is the proper binary tree. So this is the proper binary tree. And in a proper binary tree, we can have this first property. The first is E equals to I plus 1. So what is I? I is the number of internal nodes. Okay. So when we have the I, so I is the number of internal nodes. And in this case, if we take a look on this one, this is the internal node. And this is the external node. Okay. So we have like 3 internal nodes and we have 4 external nodes. Okay. So E in this case is the external node 4 equals to 3 plus 1. Okay. I is 3. And then E is 4. Then we can see that, okay, the property is correct for the proper binary trees. What about this one? N equals to 2 multiplied by E minus 1. Okay, what is the internal node? Sorry. E is the external nodes. Okay. So it means we will multiply 2 multiplied by 4 minus 1. So the result will be 7. Okay, how many nodes do we have? 1, 2, 3, 4, 5, 6, 7. So there are 7 nodes. So N equals to 7. Okay, E equals to 4. And I equals to 3. Okay. And then H is less than equal to I. So what is the H? Here is the head. Okay. So we have 1, 2. Okay. So 2 is less than equal to I. I is 3. Okay. So that is the property. What about H less than equal to N minus 1 divided by 2? So 7 is N. Okay. Then we have like 7 minus 1 divided by 2. Then we have 3. Okay. So the H is 2, which is the head, and 2 is less than equal to 3. Okay. We have another property, E is less than equal to 2 power of H. H is the head. Then if the head is 2, this one, then we have like 2 power of 2, it will be 4. Okay. So E is 4. Okay, this is correct. 4 is less than 4, less than equal to 4. And then you can check with this one. H is greater than equal to log E, sorry, log basis 2 of E. Then what is E? In this case, E is 4, so log base 2 of 4. Okay, we want to know the exponent. Then, yeah, 2 is greater than equal than 2. Okay, yes, correct. And then we have the other property with this one, log 2 n plus 1 minus 1. We know that the n is 7. So we have 7 plus 1. 7 plus 1 is 8. Log 2 of 8. Then we have 3. Okay. 3 minus 1, it will be 2. So 2 is greater than equal to 2. So those properties should be true in order to say that it is a proper binary tree. Okay. Now, if I want to check with this one, is it the same? If you want to see, this is the E plus equal to I plus 1. So what is the E and what is the I here? The external node, there are 4. Okay, so same. And the I, there are 3. And the number of nodes, there are 7. So we have the E equals to I plus 1. Yeah, the same. So we have 4 as the E and then 3 plus 1. And so on. So you can check. So the properties should be true if it is a proper binary trees. Okay. So the binary tree ADT, the abstract data type in the binary tree, we have at least 3 additional methods. So if you learn already about the tree, so the tree, yeah, this is the tree. So you already have some methods in the tree ADT. We have the root, parent, children, and the number of children. In the binary tree, I want just to know where is the left child, where is the right child, and then I want to know whether it is a sibling or not. So sibling means whether the node is in the same level, and we can update the methods. Yes, maybe it depends on the implementation of the binary tree. In the binary tree, we can have another traversal. So the traversal we know already. We have pre-order traversal. Okay, in the previously we learned about the pre-order traversal, and then we learned about the post-order traversal. In the binary tree, yeah, we have in-order traversal. So what is in-order traversal? So the idea of the in-order traversal is we want to visit the left subtree first and then go to the right subtree. So the left first and then go to the upper and then go to the left first and then next and then go to the right and then go to the right here and then go to the left part first and then go to the right and then go to the right. We call this is the method in order because we want to check if the V is the vertex has a left child. So if this one has a left child, okay. If it is not, then visit. Okay. Then after we visit and then check if V has a right child. There is no right child, then yeah, we go to the next node. So we go to the next one. Is there any right left child? Okay, maybe it's better to. Okay. So we have the in order V, okay, and usually we want to draw this one from the root. Okay, so the root is starting from here. Now we want to check if V has a left child. Okay, we have the left child. Okay, and then we will call the in order left V. What is left V? The left V is this one. Then we will do again in order and then it will check again if V as her left child. So is there any left child? Yes. Then we will go to this part and we will check in order left V. So this will be the next. We will go back to the in order V. So we will do the in order V of this one. Is there any left child? There is no left child. Because there is no left child, so we face it. So 1, is visited. And then we will ask if V has a right child, because there is no right child, then we go back to the previous one, which is 2. Okay? And then because the left child has been visited, okay, so we just visit this one. Then 2 is visited. And then we want to ask if V has a right child. Is there any right child? Oh yes, we have the right child 4. Because we have the right child, so we will do again with this in order, and then we start from the right V. The right V is 4. So the iteration of this for this recursive, again we use the in order V, and then in order V we will check whether V has a left child. Okay, there is a left child here. Then we will go to the in order left V, and then we will again recursive. After we recursive, we will check again this node. V has a left child. Is there any left child? No, there is no left child. So we will visit. Then number 3 is visited. Okay, and so on. So we will do this recursive until all the V is visited. This has been applied to the arithmetic expression, and we can make the different style of arithmetic expression. For example, here I want to include the brackets. I want to include the parentheses. In this case, I can put the operand and the operator when visiting node. So this is the operator and this is the operand. And every time I want to execute this mathematical operation, I can put bracket. Okay, I can put the bracket. Here is the bracket or parenthesis. So print the bracket before traversing left subtree and print closing bracket after traversing the right subtree. So let's see if I now if I run this algorithm, I need to check one by one. Oh, sorry. Print expression V. So it will start from the root, okay, and then if V has a left child, is there any left child? Yes. Then we print the opening bracket, and then in order left V. In order left V, so I will check what is the left of this V, and then we go here. So the in order, which is the previous one, okay, we will do this in order. So every time we will do the same thing like what we did in the previous in order. But we just need to put the opening bracket. So the result will be 2 multiplied by a minus 1. Later you can check. Plus 3 multiplied by b. Okay. So based on this recursion, and then for every time you start the left subtree, you will make the opening bracket, and every time you finish with the right node, then you will put the closing bracket. We can make the arithmetic expression with post-order traversal. What does it mean by post-order traversal? So we want to check the leaf first. Okay. So if you go to the, if you still remember this post-order traversal, you want to visit every node, but you need to start from the leaf node. Okay. So the same with this one. We want to evaluate the arithmetic expression. We can use the in-order traversal, or we can use the post-order traversal. So this is the example of the post-order traversal. We can use the recursive method, returning the value of a subtree, and when we visit an internal node, combine the values of the subtree. So let's see if it is this the algorithm. First, we want to evaluate the expression. If we want to evaluate the expression v, so this is starting v, and then we want to check if it is a leaf or not. So if it is a leaf, then return the element. But if it is not a leaf, then x will be the left, and then y will be the right. Okay, x will be the left, and then y will be the left. So we can see here if it is evaluate expression left, okay, so we can again go back here because it is still not the leaf. Okay, so we will go back here, and then until we reach here. Okay, let's, after this one we go here, and then after this one we go here. After we are in the leaf, it is a leaf, yes, return the element, so return 2. After we finish with this 2, and then we will go back here, and then we will start, we will use this operator in order to connect with this number, and then we call the y, or the right section. So we have the right one is 5 minus 1, and so on. Okay, so you can follow the flow from this algorithm to check for every number in the node, and after we visit all the nodes, it can create the mathematical expression. So the other concept that you may need to know is the Euler-Tor traversal. So the Euler-Tor traversal is the generic traversal of binary tree, and it includes special case in the pre-order, post-order, and in-order traversal. So there are 3 traversals that you need to understand. The first is pre-order, and then post-order, and then in-order. In the concept of Euler-Tor, I'm not sure if you are familiar with one of the game. Okay, there is a mathematical game. So in the mathematical game, they use the Euler-Tor. We want to visit every node, okay, and it can be, the node can be visited more than one, but the edge should be only one time. Okay. So this one is, we will walk around the tree and visit its node 3 times. Okay, so this is a special case of the Euler-Tor. And if you check this one, if it is on the left, if it is on the left, we are doing the pre-order. Okay, we are doing pre-order. If it is from the below, we will do the in order. If it is on the right, we will do the post order. So it is the combination or the special cases of the pre-order, post order, and in order. So this is the combination. If you understand the concept of the linked list, so this tree can be done with the linked list as well. So when we are trying to link the node to another node, we can create one kind of variable. In this case, we are creating the element. Okay, so we have the element to represent what is the value of this node. Let's say this one is the element, this is P. Okay. And we have another thing that we need to connect. So we need to link. Okay. So this to connect to the parent node. And then the last one will be the sequence of children nodes. Let's say this is one node. Okay. So there are three. The first is the element. And then the second is the connection to the parent. And then the other is the sequence of children. Okay. If you are looking at this node, okay, we have this is not a binary tree, of course. It is only tree. Okay. So just remember what is the difference between tree and binary tree? Okay. What is the difference between tree and binary tree? Anyone can answer? Binary tree. What is it? Why I cannot say this is binary tree? So
Binary
this is
tree has only two child.
okay. That's correct. Thank you. Oh, sorry, I cannot see. Who are you?
천수종.
Oh, Chen Suzhong. Okay, thank you, Chen Suzhong. So the binary tree has at most two children, but in this case, one, two, three. Okay, it's because we have more than two, then this is only the general tree. This is not binary tree. In order to check this link structure for trees, now let's see. We have B, A, D, F, C, and E. And then we know that P is the root. Okay. P is the root. A, C, E, F are the leaf. And then D is internal node. So if I want to define P, then there should be three elements. First is the element value, which is P. And then is there any parent of P? No parent, because it is the root. And then the last section in this link is sequence of children node. Okay. So here it is the sequence. So the first, the second, and the third. Now you will see that we have three nodes. The first node is going to A, and then the second node is going to D, and the third node is going to F. Okay, and then we know that this first is the element. Now the element is A, and then the second one is the parent node. So what is the parent node of A? The parent node is, we're choosing the B. B is the parent node of A, and then also D has a parent node of B, and then F has the parent node of B. What about the last one in A? It is empty because there is no children. Okay. What about T? In a T, we have we have two children. Okay, and it is the sequence. The sequence first is going to C. So this is the C, and then this is the link of the tree. So it linked to another element, and then it will be empty because it is the leaf. And then this is the element value, which is E, and then it goes to the parent, and then this is empty because there is no child. Okay, so this is the link structure for trees. If we want to use binary tree, okay, is there any difference between the link structure for tree and binary tree? Yes, we need to consider one more factor. What is one more factor? In this binary tree, we have element, we have parent node, yeah, and we need to specify where is the left and where is the right. We need to specify where is the left and where is the right. If it is just a general tree, then you need to have sequence. So the sequence represents which one is the first, which one is second, which one is the third. But if it is binary tree, you only have two, left and right. Okay. So in this case, if I have this tree, okay, so the tree here is B is the root, and then A, C, and E is the leaf, okay, and we have one internal node. So the link structure is, yeah, we can present like this one. The left one representing the left node, and the right one representing the right node. Okay, and then if there is nothing to be connected to the parent, then it will be empty. And then if you have children, then you will have an arrow. Okay, so that's the the diagram to represent the link structure for the binary trees. So if we know that B has the child A and has a child B, and then A, there is no left and there is no right children. There is no left, there is no right children. And then what about D? After we have D, so D is connected back to the B, and then the left child is C and the right child is E. Okay. And then for C, we have one parent which is D. For E, we have one parent which is D, and then yeah, it just shows the element. This is C and E. Okay. Now we can also try the binary trees using array. Just remember array. When we have array, you will see something like this. Okay. Uh, in the exam on the e-class, so you will have you had one problem about the queue. So the queue is in the list, and then whenever we run the queue, it will empty the existing location and then put the element in other position of the array. Okay. So the array concept is having the location index, So the location index start from 0. Okay, the location index start from 0. Now, suppose I have this binary tree, and then like say I have A, B, yeah, this is D, E, F, C, J, G, H, okay. Now, I want to put the A in the rank V. V is the node. Now, we call it, this is rank, okay. Rank, it is a kind of formula. So we can calculate the rank according to formula. If it is root, then the rank is 1. If it is a left child, then it is the rank of that node will be 2 multiplied by rank of the parent node. If the node is in the right, then if the node is the right child of the parent node, then the rank of the node will be 2 multiplied by rank parent node plus 1. Okay, so what does it mean? Let's see. We know that every time we deal with the tree, it will start from root. So it starts from root. What is the rank of the root? The rank of the root is 1. Okay. Then in the A index 1, the element A will be saved. So maybe you will have question, Professor, why we start from 1? Why don't we start from 0? Yeah, that's the formula about the multiplication. So if it is multiplication, then you cannot start with 0. So we will just put the 0 as length. Okay. That's why this is the index 0, it is blank. And then after we have the rank root equals to 1, and then we have the next left child. Okay. We have the left child, which is B. So the formula will be, the rank of the node will be 2 multiply rank parent node. So what is the rank of the parent node? A. What is the rank of A? It is 1. So the result of this rank node will be 2 multiplied by 1, and we will get the A index 2. Because 2 multiplied by 1 is 2. So the index 2 and the value will be B. Oops. Okay. And then we go to the right. If the node is the right child of the parent node, then the rank will be 2 multiplied by the rank of the parent node. So the rank of this A is 1. Then 2 multiplied by 1 plus 1. 2 multiplied by 1 plus 1, then it will be in the index 3. Okay. So the index 3 will be D. So the index 3 will be D. Now we will go to the next, which is here. We have, because the root already set as 1, so we will go to the next here. If node is the left child of the parent node, now we go to E. So E is the left child of B, yes. Then the rank of the node B, rank of node E is 2 multiplied by the rank of the parent node. So the rank of the 2, what is the rank of 2? The rank of 2 is, the rank of B, The rank of B is 2. So 2 multiplied by 2, then the result is 4. So the index 4 will be for the element E. Okay. And then what about F? F is the right child. Because F is the right child, then we will have the formula 2 multiplied by rank parent node plus 1. What is the parent node? The parent node is B. So the rank is 2. So 2 multiplied by 2, which is 4, plus 1. So we have the index 5. And the index 5, oops. Oh, okay. So the index 5 will be F. Okay. Now you can continue to the next, which is C. And C is 6. How can we get 6? Because it is 2 multiplied by the rank of the parent node. The parent node is 3. Then 2 multiplied by 3 is 6. What about J? J is in the right child. So we will do the 2 multiplied by the parent node, 2 multiplied by 3, and plus 1. So the result will be 7. So the index 7, okay, will be the J. Okay, and so on until you finish with all the nodes. So in this case, G is the right, no, sorry, G is the left. So 2 multiplied by the rank of the parent node, 2 multiplied by 5, so it means 10. And then H is 2 multiplied by a parent node, which is 5, plus 1, so it means 11. Then, yeah, you can see that this one, oops. So the array will be something like this one. 0 is blank, 1 is filled with A, 2 is filled with B, 3 is filled with D, and so on. And then the element 10 will be filled with G, and the element 11 will be filled with H. Now, my question is, where is 9? Where is 8? There is no 8, there is no 9. So it means the location index 8 and the location index 9 will be blank and no problem. Okay. So that's the case when we can, if we want to use the array-based representation of binary trees. Okay. I guess we can